Now, let's take a closer look at how local token validation actually works. As we have learned in previous lessons, local token validation is possible with JWTs because they are self-contained tokens that include a signature. This is the third part of the JWT token. The signature plays a critical role in ensuring the integrity and authenticity of the token, meaning it confirms that no one has tampered with the token's validation information. So the real key to local token validation lies in understanding how this signature works. Once we grasp this mechanism, we'll have a solid understanding of how self-token validation functions. In general, there are two types of signing algorithms used to create these signatures: symmetric signing and asymmetric signing. In simple terms, symmetric signing involves a single shared secret key that's used by both the sender and the receiver. The same key is used to sign and verify the data, which means it must be kept secure by both parties. On the other hand, asymmetric signing uses two keys, a private key and a public key. The private key is kept secret and is used by the sender to sign the data. The public key, which is available to anyone, is used by the receiver to verify the signature. Let's start with the symmetric signing approach. Imagine a scenario with Bob and Alice. Bob and Alice often message each other, but they want to ensure that their messages are not tampered with by an evil guy who wants to cause trouble in their relationship. To protect their messages, Alice and Bob share a secret key called a shared secret. This key must be kept secure by both of them. Now, Bob writes a message to Alice, "Hi Alice, I miss you," and then signs it using the shared secret key. This signature allows Alice to verify the integrity and authenticity of the message, ensuring that the evil guy hasn't tampered with it. When Alice receives the message, she uses the same shared secret key to verify the signature. And there we go, she can now be sure that the message truly came from Bob. Now let's relate this scenario to a JWT access token. In this analogy, Bob represents the OAuth 2.0 authorization server, which has a shared secret key. The message is like the JWT token that authorization server creates and signs with the shared secret before sending it to Alice. Alice in this case is the resource server. She receives the token via the OAuth 2 client and needs to verify its signature locally using the same shared secret key. Now imagine the evil guy as a man-in-the-middle attacker who tries to manipulate information in the JWT token, for example changing the scope from orders read to orders write. Unfortunately for him, the resource server catches this during the local signature validation process, which ensures the token's integrity. The verification fails because the information no longer matches the original signature. The evil guy would need to re-sign the token with a new signature that aligns with the altered information. But he doesn't have the shared secret, which makes him very sad. We mentioned earlier that the shared secret must be kept secure, but here we encounter a significant problem. The authorization server often doesn't trust the client applications, and for good security practice it should not. When there are multiple clients, let's say 100, sharing the same shared secret for token verification can pose a serious security risk. This is why asymmetric signing of tokens is commonly the safer solution, as it allows each client to verify the token without exposing the critical secret. But how does asymmetric signing work exactly? Asymmetric signing is based on two keys, a private key and a public key. In this scenario, Bob, who writes the message, has a private key, while Alice, who receives the message, has a public key. The public key is publicly available for anyone or any client that wants to verify that the message truly comes from Bob. However, the private key must be kept secure. Similar to the previous scenario, Bob writes a message to Alice, "Hi Alice, I miss you," and signs it with a private key. The signature allows Alice to verify the integrity and authenticity of the message, ensuring that the evil guy hasn't tampered with it. When Alice receives the message, she uses now the public key to verify the signature. And there we go, she can now be sure that the message truly came from Bob without needing to get the private key that signs the information. Bob represents the OAuth 2 authorization server, which has the private key. The message is like the JWT token that the authorization server creates and signs with the private key before sending it to Alice. Alice is the resource server. She receives the token via the OAuth 2 client and needs to verify its signature locally using the public key. This public key could be stored in each resource server that needs to validate the tokens. Alternatively, the authorization server could provide an endpoint that allows resource servers to fetch the public key as needed. This approach is more practical because if the authorization server changes public key, the resource server can automatically fetch the updated key from the endpoint. In many frameworks like Spring Boot with Spring Security, the key will be cached when the application starts. And if unknown signature is countered, the application will call the endpoint again to update the public key if necessary. Now, the evil guy, the man-in-the-middle attacker, tries again to manipulate the information in the JWT token. For example, changing the scope from orders read to orders write. The verification fails again because the information no longer matches the original signature. The evil guy would need to resign the token with a new signature that aligns with the altered information. But he doesn't have Bob's private key. Even if he has the public key, he can only verify messages but not sign them. That's why even if we have 100 OAuth 2 clients, each with a public key, we ensure that only our trusted authorization server can sign the tokens. That's why we use the asymmetric signing method for signing OAuth 2 access tokens. The resource servers need only the public key to validate the JWT token, where the authorization server is the only party that possesses the private key used for signing the tokens.